So section 4.5 is the last section in chapter 4. It's the last section we're going to cover before we test next Thursday. It'll be 4.1 through 4.5. So 4.5 is kind of putting all the skills we've learned in the previous section together to solve equations. Now, a little bit has shown up in the previous sections in terms of solving equations, but those were kind of easy examples. And this section, 4.5, is entirely dedicated to the pursuit of solving these exponential equations and log equations. And so they're going to be a little bit more fun than the ones we've seen so far in the previous sections. All right, so first of all, we're going to be looking at conditional equations. There's several types of equations. You have identities, which are true for all values of x in their domains, like the one we did yesterday in the worksheet when we were proving that the left side equaled the right side. We call that an identity. It's always true. Then you have name equations like f of x equals. That's a name equation. And then you have contradictions like 5 equals 7. That's an equation that's not true. These are called conditional equations. And when you're tasked with a conditional equation task, it's usually to find the conditions in which the equation is true. Or, in other words, solve for the indicated variable. So that's what we're going to do. So if you look at this one right here, this is a real basic conditional equation of the exponential variety. What makes it an exponential equation? It's got a numeric base and a variable where? In the exponent, right. So if you're trying to solve this one, you're looking for powers of 3 that give you an 11. And this is not one that we can necessarily solve directly without the help of some other tools like a calculator or logs, as you'll see. But at least we know what a reasonable answer is, right? We know that x has to fall between which two integers? 3 and 4? Actually, 2 and 3, yeah. Here's how you know, because 3 squared is 9. That's too small. It's not quite 11. And 3 cubed is 27. That's too big. So you know it's got to be 2 point something. And you think it's going to be closer to 2 or closer to 3? It should be closer to 2, yeah, because 9 is closer to 11 than 27. So it's 2 point something. All right, and that might be good enough for some people, but we want to get the exact answer, all right? So that's what this section is going to teach us how to do. So let's jump to example 1. Same equation, we want to solve for x. All right, so I'm going to rewrite it down here, which is basically putting it on my workbench. So in order to systematically solve for x, so that we're not guessing and checking, that can take a while, we have our exponential factor isolated. So what we want to do now is somehow get the x out of the exponent onto the ground floor, because our goal is to have x equals and then our answer. Right now it's trapped as an exponent with a base of 3. How do we undo exponentiating base 3? Logging base what? 3, yeah. So I'll show you a couple methods to do this. Method 1, we'll call this one method 1. If you take the log base 3 of both sides, you have to write it on a separate line because the log goes in front. So it's log base 3 of 3 to the x equals log base 3 of 11. Take the log of both sides. Now the reason this works is because on the left side, what is log base 3 of 3 to the blob in general? The blob, yeah, in this case the blob is x. Exponentiation and logging are inverses of each other with the same base. And then on the right, you end up with log base 3 of 11. Now, log base 3 of 11, remember, is a number. There's no variables in it. But we don't really know what it's equal to exactly because it requires some kind of calculator or tables. So that is an answer. And if this were a test question, maybe a multiple choice question has log base 3 of 11 as an answer choice. But in this class, we like to use one base above all others, and it's the natural base e. So I would probably put your answer in terms of base e. So that's no big deal. If you got this answer at the end, let's just go ahead and convert it to base e using the change of base formula. So it should be the natural log of 11 over the natural log of 3. And I like that answer better. It looks less clean because it's a quotient, but it's in terms of base e, and that makes us all feel better, right? Now, method 2 is going to be a method because if our goal is to have it ultimately in form of base e, then we can actually use base e from the beginning instead of using the particular base of the exponent. So method 2 is the one that I would encourage you to use. So we still start off with 3 to the x equals 11, But now, instead of taking log base 3 of both sides, we're just going to take the natural log of both sides. The natural log of 3 to the x equals the natural log of 11. Now, unfortunately, the left side is not just plain old x like it was previously, but we're still able to get the x out of the exponent by using property number 3, right? Which says you could bring the exponents on the argument out front. So that becomes x times the natural log of 3 equaling the natural log of 11. And now I can solve for x. Currently, I'm multiplying it by the natural log of 3. So to undo multiplication, we do what? Division, yeah. And you don't even have to show that. You can just do it in your head. So the natural log of 3 divides out on the left, and we end up with the natural log of 11 over the natural log of 3 as our final answer. And notice we get the same thing ultimately that we would have got over there. So there you go. I would encourage you each and every time then to use base E from the very beginning instead of going from problem to problem using whatever particular base is there. Not that it's wrong, but we just prefer base E. All right, now if you're curious what that's equal to, now you can go to a calculator. I'm not going to show it projected up there, but if you type it into your calculator, natural log of 11 divided by natural log of 3, it is approximately equal to 2.182 if you truncate and 2.183 if you round. So as we suspected, it's right there. It's at 2.1 something, between 2 and 3 and closer to 2. Now, because this is really a trivial answer after you've done all the wonderful work and get the exact answer, for the rest of the section, I'm not even going to bother getting the 3 decimal approximation. Because I'm assuming if you can get down to the simplified exact answer, any monkey, if you task it with this, can type in the answer you get and come up with a 3 decimal approximation. It may take them a little while after they're done writing all the works of Shakespeare, but they'll eventually type it in. All right, good. Any questions on that one? We got our toe wet now in the mathematical waters of exponential equations. All right, so let's look at this box down here. This one was actually an advanced method, taking the natural log of both sides. The first method that we've encountered in previous sections for solving exponential functions is what I call the GTBTS method, which is short for get the bases the same, the GTBTS method. So here's what it says. If b to the x equals b to the y, that is, if you can get the bases on both sides of your conditional equation the same base, of course, where you have legal bases between 0 and 1 or greater than 1, then you can equate their exponents. It's the exact same thing that we did if you were to take log base b of both sides. But what I'm saying here is you don't even have to show that step of logging b both sides. You could skip the step and just say, all right, if I can get b to the blob equals b to the blob, then blob equals blob. Drop the bases and equate the exponents. Let's try that method out on example 2. By the way, we could not do that on this one, right? Couldn't get the bases the same because 11 wasn't a nice perfect power of 3. Okay, so come over here to example 2. The instructions are the same for all three. Solve. So we got 9 to the 2x equals 27 to the x minus 1. So this is a conditional exponential equation. We have an exponential factor on each side. You could jump in and take the natural log of both sides, but before you do that, you should look to see if you can get the bases the same, because ultimately it's going to be a little bit easier. I can't write 9 as a power of 27 very easily, and I can't write 27 as a power of 9 very easily, but what do you notice about 9 and 27? You can write both of them as nice powers of 3. All right, so that is your task. Let's choose base 3. We'll choose 3. So on the left side, I get 9 to the 2x power. I'm just going to replace 9 with 3 squared. And on the right-hand side, I still have 27 to the x minus first power, but I'm going to replace 27 with 3 cubed. And notice the parentheses there. Now I can use the rules of exponents. When you're exponentiating, it turns into multiplication. So 3 to the 4x on the left, and 3 to the 3 times the quantity x minus 1 on the right. Now at this point, you have the option of writing it as 3 times quantity x minus 1, or as you're writing it, you can feel free to distribute 3x minus 3. It's up to you. But now I have 3 to the blob equals 3 to the blob, so guess what? Blob equals blob. Now I'm going to distribute 3x minus 3. Okay, you don't have to show the line where you're taking the log base 3 of both sides. You can just use a little theorem. It works because exponentials are 1 to 1. Now we're back in Algebra 1, maybe on day 2 of Algebra 1. Remember that? Solve for x. Okay, we'll bring the 3x across, and I get x equals -3. And we're done. That's a systematic approach to solving these exponential equations by the GT-BTS method. Notice I'm working straight down. Every line is equivalent to the one above and below it. The bottom line is considered your answer. So there's no need to put a box around it, okay, unless you want to. It's fine. It's fine to have it. If you're proud of it, put a box around it. If you're really proud of it, kind of put a ribbon on it and maybe give it away as a Christmas gift. All right? So if it's the bottom line, you don't need to box it. All right, let's check out letter B. It's an exponential equation. I got a variable in the exponent. I have a base of 1/5 on the left and a base of 4 on the right. I'm not sure I can write base 1/5 and base 4 in terms of each other, but that's a moot point right now because you're not even at that stage. You've got this 100 dude that's in front of the exponential factor, and he's kind of ruining the get the bases the same party. So your first step in the GT-BTS method is to isolate your exponentials or your exponential factors. So in the first example, they were already separated. We had one on one side, one on the other. Here I have the 1/5 x to the 4th. It's being multiplied by 100. So how do I get rid of the 100 if it's currently being multiplied? Divide. So if I divide both sides by 100, you get 1/5 to the x 4th power equals 4 divided by 100. And now you've got your bases isolated. The left side is 1/5. The right side's base is 4 100ths. 4 100ths. I'm looking at that, and I'm having this irresistible urge to call it what? 1/25. Yeah. So simplify early and often. Now you're in business. It wasn't going to be very easy to write 4 100ths as a power of 5. But once we simplify now, I've got a 1/5 on the left and a 1/25 on the right. So you can write both of them now in terms of base 1/5 if you want. In that case, the left side would be already ready to go, and 1/25 is the same as 1/5 to the what power? Squared. Okay? So now we have 1/5 to the blob equals 1/5 to the blob, so we can equate the blobs. X divided by 4 equals 2. And now all you have to do to solve for x is multiply both sides by 4, and you get 8. Nice, I agree. So if you don't have to get the logs involved, don't do that, okay? It's easier if you can get the bases the same. Now let's say you don't like fractional bases, right? I get it. Here's what else you could do. You could say, all right, I can write 1/5 and 1/25 both as powers of 5. So that would be 5 to the -1st to the x 4th power equals 1/25 is 5 to the -2nd, right? 1/25 is 5 to the -2nd. Now if you raise the power to power, you multiply, you get 5 to the -x 4ths equals 5 to the -2nd. So now it's 5 to the blob, 5 to the blob. So now you get -x over 4 equals -2. And now instead of solving by multiplying both sides by 4, you multiply both sides by -4. And you get +8. There you go. So if you don't like fractional bases, just flip them and change the sign of the exponent. It'll work. As long as the bases are the same, it will work. All right, sweet. Letter C. Woo. Look at that one. That is totally radical, right? For a couple of reasons. It's got 2 radicals, and it looks fantastically exciting. You walk up to that one, and you know there's a good time involved, right? So if we're going to try and get the bases the same, notice on the left side, what base would you be leaning towards on the left side? 4 would work, right? Because you can write 1/4 as a power of 4. You can write 16 as a power of 4. On the right side, what base would you be leaning towards? Probably a 2, right? Well, because you can write the right side as a power of 2, and you can write the left side as a power of 4, you could then also write the left side as a power of 2. So it's a matter of finding that common base that everything in the problem can be written in terms of. So let's go ahead and choose base 2. Not even base 1/2. We'll choose base 2. So now all you have to do is go through on each line and try and write everything as 2 to some power, 2 to some power. And we'll work towards the final answer. All right, so 1/4, that's the same as 2 to what power? -2. At this stage, in this level, in this game, you should be able to look at 1/4 and call it 2 to the -2nd in your head. If not, take more steps. The next factor, that's the cube root of 16. Well, 16 is 2 to the what power? 2 to the 4th power. But because it's the cube root of it, it's then that number raised to the 1/3 power, so it should be 2 to the 4/3. Again, take more steps if you need it, but that's where I'm hoping you can be, looking at the cube root of 16 and knowing it's 2 to the 4/3. Now that is still raised to the x plus 4th power. So we do as much as we can, but not too much. On this side, the numerator is the 5th root of 8. Well, that's 2 to the what power? 3/5, right? 5th root becomes the denominator. And the bottom is just 2 to the 1st. I'll put a little 1 there. And it's raised to the 2x minus 1st power. All right, that's about all we could do. We do a little bit of something as we go from left to right. Now we go down to the next line. Before I can combine the exponents on these two factors of 2, your Aunt Sally says what? Yeah, you got to do that first. Exponentiation comes before multiplication. That's the excuse, comes before my. All right, so the first factor is he's just going to be rewritten. There are worse things that have happened to you. And now when we raise a power to a power, we multiply. So at this point, I'm going to go ahead and distribute the 4/3 to the x and the 4. Because ultimately, you're going to want everything expanded out. So that'll be 2 to the 4/3 x power plus 4 times 4/3 is 16/3. And again, notice if you're writing in the exponent, they've got to be a little bit smaller and make sure that everything is staying perfectly level. If you tend to have more terms in the numerator or in the exponent, those terms down the line can't support on the cantilever. They tend to fall down on the ground floor. So if you want, go ahead and put an extra set of parentheses around them to keep them up there. Better to have them and not need them than to need them and not have them. All right, now on the right-hand side, we can do a couple things like we saw in the beginning of the year. You can distribute the 2x minus 1 to either both of those exponents, or you can work from the inside out, which is what I think I'm going to do. So I'll leave the 2x minus 1 out there. Now when we're dividing, what do we do with the exponents? Subtract. So we got 2 to the 3/5 divided by 2 to the 1st. That's 2 to the 3/5 minus 1, which is -2/5. Right. So all that work we did at the beginning of the year, it's paying off right here. So we did as much as we could. Now we go down to the next line. Now I'm ready to combine these exponents by adding them because the bases are the same. So we get 2 to the 4/3 x plus 16/3 minus 2. And I'll go ahead and put parentheses around that because that's 3 terms. I don't want that -2 to fall down. And on the right-hand side, we got a power raised to the power, so I'll distribute, and you get 2 to the -4/5 x. It turns into a positive 2/5. How did I go from 3/5 to 2/5? Oh, I'm subtracting right here, yeah, because we're dividing. And so I subtract the exponents, right? 3/5 minus 1. So 1 is known as 5/5. So what's 3/5 minus 5/5? -2/5. Yeah. Yeah, you're going to have a lot of fractions here, so make sure you're writing big enough to read your own writing. Inch by inch, it's a cinch, you know. Put ones there as exponents to help you or something, whatever. Parentheses as well. So now we've worked hard to get to this level, and it's going to pay off. Now we got 2 to the blob equals 2 to the blob, so we can equate the blobs. So the left side now becomes 4/3 x, and we can combine these two numbers, 16/3 minus 2. 2 is how many thirds? 6, right? So it's really 16/3 minus 6/3. 16 minus 6 is 10/3. Yeah, so you get 10/3. Equals, we could drop the 2 on the right-hand side, and we're just left with -4/5 x plus 2/5. And now we're back in Algebra 1, but not first day or second day. This is late Algebra 1. You got a bunch of fractions. So at this point, again, you have two options. You can either embrace the fractions, which is what you do if you like fractions or you're not good with fractions. Or if you know what you're doing and you don't need the extra practice with fractions, you can multiply both sides by the LCM of your denominators, which is what? What's the LCM of 5 and 3? 15. So if you multiply the whole right side by 15 and distribute, the denominators will divide out. And if you multiply the whole left side by 15 and distribute, the 3's will divide out. I'm not going to do that, but if you want to do that, go for it. I'm going to embrace the fractions, not because I'm bad at them, but I love them, love them, love them. So here we go, very carefully. I'll bring that negative 4/5 over to the left-hand side. So we have a 4/3 x, and joining them now is positive 4/5 x. Good to see you, old friend. 2/5 now becomes the welcoming committee on the right-hand side of the equation, who is now welcoming his new pal, negative 10/3. All right, so I'm going to shrink this down because I need a little bit more room. All right, so now it's just a matter of combining fractions. 4/3 plus 4/5. Remember, you could do the crisscross applesauce. Here's what it looks like. A over B plus or minus C over D. This will always give you a common denominator. It won't always be the least common denominator. You take your diagonal product from the top left first. That's AD. Then you take the sign of whatever it is between them, and then you multiply by the other diagonal product, BC. All over the product of the two denominators, BD. It's real fast, okay? But you got to start in the top left because subtraction is not commutative. So let's see what that looks like over here. You have a 4 times 5, that is 20, right? Plus 4 times 3. What's 20 plus 12? 32. So our numerator is 32, and then 3 times 5 is 15. So you get 32/15 x. Equals. We'll do the same thing on the right-hand side. Subtraction, so we've got to be a little more careful. If we start on the top left, we're okay. So 2 times 3 is 6, minus 10 times 5 is 50. What's 6 minus 50? Negative 44. All over the product of your two denominators, 15. Now, if you don't want to do it that way, you can do it like you did in little school. You can multiply the 2/5 by 3 over 3. You can multiply the 10/3 by 5 over 5. That's getting a common denominator, and then you add them straight across. Whatever you want to do. That's not the obstacle at this point to mastering this question. If it is, you need to go off and practice on the side somewhere. Now we go to solve for x by multiplying both sides by the reciprocal of 32/15. So what's on the right-hand side, I'll just rewrite, times the reciprocal of the left side, which is 15 over 32. So there is the answer. X equals that. But we could do a lot better than that. We could pretty X up like he's getting ready to go out to Wasselfest tonight or something. It's going to be a cold Wasselfest. That's going to be good. All right, what happens with your 15s? They don't cancel, Vaughn. What do? The 15s. No, they don't cancel. ¿Cómo se dice divide out in English? They divide out. Yeah, very good. Yeah, I think they call that a cognate, right? Dividing out in both languages. They divide out. They don't cancel. They divide out. And you're left with negative 44/32, which also simplifies. What is a factor of both 44 and 32, or the biggest factor would be great? 4. I can see that 4 goes into both of them. But if you're not sure what it is, you know they're both even, you could simplify more than once. If you factor out a 2, you get negative 22/16. And you're like, they're still both even. So I can factor out another 2, negative 11/8. And that's fine if you have to keep going more than one step. If you knew that was a 4 right away, you could get straight to negative 11/8. And there is your final answer. Now, I'm going to erase it over there because I really want to work down each and every time. I was going to run out of room, but I'll make it work. So negative 11/8. When you work straight down again, it's considered that your bottom is your final answer, so there's no need to box it. Now, if you were doing this by the guess and check method, you're probably still checking, and I don't know if even a negative 11/8 is on your radar of things to check, right? So that's why we have algebra. Algebra is a systematic algorithm that we can use the same procedure every time to get down to declaring x equals our answer. Yeah. So anyway, I think that's a great place to stop for today because the fractions filled our hearts, and there's no room for more joy today because it's full of fractions. All right? Tomorrow we'll pick up with example 3, and it'll look more like what we did on this problem that we started off the section with. You're not going to be able to get the bases the same, and so that's when the problems get a little more loggy